Thank you so much. Thank you for having me here. Okay. So today's material, let's start from the basics. We're standing on the shoulders of giants. All the material that you're going to see today is just an excerpt from a workshop that Francesca Campoy and myself have collaboratively developed and given over the last couple of years. So credit where credit's due. And the second thing is that my goal for today is for you all to leave with the skills for how to profile a Go program. And perhaps if you've used some of the tools, maybe, just maybe, you won't have used all of these. So hopefully everyone will come away with a little bit more knowledge than they did before. And because it's the afternoon, it's the second day, I thought we'd try some live coding. Let's live dangerously. So we don't need Keynote anymore. Let's embiggen that a little bit. Normally I say, is that big enough to see? But this is like a giant screen, so we're all good. So the task, let's say we've been given, is to write a program that just counts words in a program. We might write something like this. We read the file, we open the file we're passed in. We make a counter of the number of words. We also have to keep track of whether we're in a word or not. So we're going to, for each character in the file, we read it, we check if we get to the end of the file. If not, we ask, is it a space? And if it's a space and we're not in a word, then we found the end of a word. So we increment the number of words we found, set the word state to false, and then go around again. So basically we're not so much counting words as we're counting the spaces between words and collapsing them if there happen to be multiple spaces. Is everyone roughly okay with this program? Okay. So if we're going to count some words, we need some words to count. One of the great things about the internet is we have Project Gutenberg, which provides classic literature that happens to be quite big. That's 1.2 meg of text. And Project Gutenberg is not just useful for examples like this. Also, if you work in a pen testing role, or you just work in a role where your company makes things that have text boxes, feel free to put that in there as well. That really helps. Okay, so now we have our program, and we can ask it to count how many words are in Moby Dick. So around about 181,000 words. I should have started my timer, by the way. That's okay. Okay, but the other thing you noticed is that it took a few seconds. So we could ask how long did it take? And today, on this machine, on battery power, at this altitude, at this humidity, all those factors that involve how fast your fans are spinning, how fast the clock speed is, took about 1.1 seconds. Okay. And the next question we could ask is, well, okay, is that good? Like, it's almost a second a megabyte. Is that good? And one way I might approach that is to compare it against something else. This is Unix. We have a command called WC, and WC takes a -w flag, which says, give me the count of words. So we can ask it to, I didn't even time that, but it was so quick. Now, I want to mention two things. One, what WC considers to be a word and what my program considers to be a word are not the same. This is not relevant for what we're going to do today. This is, they just have a different way of deciding what's a word and what isn't. But importantly, both of these programs, to count the number of words, has to read the whole file. So structurally, they do the same thing, even if they probably have slight differences. But the more important thing is you can see, obviously, this program ran in, well, let's just round that up to 0.01 of a second, whereas mine took 100 times longer. So faced with these things, we can say, well, all right, we need to improve the speed of the Go program. Like, we should be able to do a bit better like this. And how are we going to do that? How are we going to know where our program is spending its time? And the answer to that is, just like the old proverb, measure before you cut. So let's have a look at the program. And I'm going to, now profiling in Go, you can do it manually. It's a bit annoying. So I'm using a library. which is just going to set that up for me. So we're asking for a CPU profile, and the other one is profiling path. We're just going to write it to the current working directory. Otherwise, it goes in that long directory that Mac calls the temp file. So rebuild the program again. We have to build it again because we don't want to time how long it takes to compile it. We don't want to say go time, go run. So now if we run the words program again, you can see the library that I'm using prints out CPU profiling enabled, and then also captures when it finishes. So now we have a profile, and this is great. How do we investigate profiles in Go? We use the Heap Profiling tool, which has this lovely HTML interface. So we can load up our profile in that. Let me just make that a little bit bigger. And that was not what I was expecting to see. Let me just quickly check that I did everything right. Yep. Just grab that profile again. That was it. Okay, let me just make that a little bit smaller. So there are two parts to this profile. The way you read these profiles is you look at the big boxes and the big arrows. So obviously there are two parts to this program. We have most of the activity on the left-hand side and a little bit of activity over there. But we can see, for example, here, this is 97% of the runtime. So don't worry about the stuff on the right-hand side. And we can follow down. The fact that it's always 0 of 830 milliseconds is saying that the time isn't spent in this function, it's passed down. It's passed down. And so if we keep tracing this down, get down to syscall.read, read, and it's saying that 97% of this program is spent doing syscalls. So maybe that's the answer to the problem. Like maybe that's why our program is slow. Doing a syscall in Go is too slow. Who thinks that's the answer? Well, there's actually a little clue up above here that suggests that maybe syscall isn't too slow. We can see that we start with read byte. So every time we want to read a byte, we're calling file.read, and that's calling file.read, and that's doing some read mechanics and falling down to the syscall. So maybe one of the things that we're doing is that we have to read every byte, but every one of those is falling through to syscall. And if we look at our program, let's go back to our program, that's exactly what we see. We call read byte, and read byte creates a buffer of exactly one character, passes it to read, and then returns that character. And something which sometimes catches out programs coming to Go is that our file I/O is not buffered by default. If you want it to be buffered, you have to buffer it yourself. And this is probably what the root cause is. We need to make and then pass the buffered reader. Right, so now, instead of just passing the raw file handle, we're wrapping it inside a buffer. So hopefully if that buffer is working, we should reduce the number of syscalls that we see because we're reading in larger amounts. So I can use the B there. Okay, so let's time our program again. Okay, much better. Like that's nearly half the time there. It is important to note that profiling actually can add some overhead. We'll see later how much that overhead is there. But we see we've gone down to nearly a third of what we were before. That's pretty good. So let's have a look at the CPU profile and see if that matches what we saw before. Before, remember, it was just this long chain of every time we read a byte, went through the syscall. Let's have a look at the profile. And now, the profile is different. It's much different. We can see that read is much, much smaller here. And in fact, most of the time in our program is spent in something that we didn't see before, probably because it was much smaller, this thing called malloc GC, which is coming from new object, which is coming from read byte. So maybe we've improved the performance of our program a little bit, but maybe some of the performance is now not due to doing reads, but actually memory allocation. And so what we can do is we can adjust our profiling to say, rather than take a CPU profile, let's take a heap profile. And heap profiling doesn't, if you're from the Java school where you take a heap dump and then you kind of pour over it, a heap profile, in fact, gives you stack traces that lead to allocation. So it doesn't tell you who's using the memory, it tells you who allocated the memory. So we can fix the program. And all we need to do for a memory profile is just change this to memory profile. Now, two things have happened here. One, you notice that the time changed, and this is because different profiling, as I said, has different overheads. Memory profiling works slightly different than CPU profiling. CPU profiling sets up a counter and interrupts the program and grabs stack traces. Memory profiling, as we can see here, enabled the rate of 4096. This is sampling. So every 4,000 allocations, we grab a stack trace. And because of that, you can see that the overhead is lower. So let's have a look at that. Now, the way we look at a profile is the same as a CPU profile. Just double check that I did everything right. Yep. Just close a few of these windows. Nope, this one is not happy. Let me... Okay, I think that was, I think I had forgotten to recompile beforehand. That's actually a number that I'm more expecting to see. Okay, let's see if this is going to work any better beforehand. Still nothing. That's super embarrassing. This is not the... Okay, what I might do is we can increase the profiling rate. That is, rather than every 4096, we can say, I want to profile every allocation. This is why I say mem profile rate 1. So grab that. Hopefully this profile will have something useful in it. Thank God it does. Possibly we were sampling at too low a rate, and so we just didn't grab enough useful samples before the program exited. But what can we see here? So we can see that all the allocations, 98.5% of them, are happening in this read byte function. There's a few other little ones here. In fact, we can kind of see something related to the profiling, but all of the allocations are happening in read byte. And there's something else that is quite telling. 1.2 meg of allocations is happening in read byte. That's exactly the same size as the input text. So we know that the number of allocations in this program is based on the size of the input that we give it. So let's go back and have a look at the program and ask why is every one of these calls to read byte allocating some memory. And in fact, we can go to the source, make that a bit bigger, and we can actually see the line that the allocation is happening on. This var buff an array of 1 byte. It's kind of strange. Like why is this 1 byte allocation causing so much garbage on the heap? And the answer is that because we slice it, we take a slice and we pass it to this IO reader. Now, in Go, interfaces are, like anything can implement a reader, and so the compiler doesn't know on the other side of this interface what is going to happen to that buffer. We know that the reader that we pass to it isn't going to do anything special with it. It's not going to keep a reference to it or anything like that. But in general, the compiler can't know that. And so what's happening is that every time we allocate this 1 byte buffer, it's escaping to the heap. So every time we call read byte, we actually push 16 bytes of allocation onto the heap. So there's one way we can fix this, and this is a very common trick, which is we just pull the buffer out of there. Now, in doing so, we've done two things. This, because we're now no longer allocating this buffer over and over again, we're just reslicing the same buffer, we should reduce those allocations. And we'll check that, and then I'll come back to something else about this program. So, grab it. Now, let's just compare that to the previous tab, which you remember was just this one allocation here. And it kind of seems like I've made this worse. Like, look at all the stuff on the screen. But if you actually look, these allocations are tiny. In fact, the biggest one, the biggest box, is 4 kilobytes. That's coming from the buffer, our new reader that we added. So because we have the memory profiling turned up to a very high level, it's recording all of the allocations. And now we've removed this huge allocation that we had before. Now all we can just see is just like these little stones. So this is kind of telling us that we have reduced the allocation of this program a lot. And just to go back to the original question, let's take out the profiling so that we're not paying for that overhead. So now you see when ignore the first run, that's like operating system caching stuff. So now we're down similar to what WC did. With at least one order of magnitude. I mean, if you round that up to 0.01, we're at 0.02 and a bit. So we've improved the performance of this program by nearly 2 orders of magnitude, just with using the memory profiler and the heap profiler, and just taking a look at the results that it tells us. Cool. Now, before I move on to the next example, I want to come back to the question that I had earlier, which is, I've not just improved the performance of this program, but I've actually changed the behavior of read byte. Previously, read byte behaved like this. It allocated the buffer it needed, it passed it to read, and then returned the value. In attempting to improve the performance of this code, I've changed one very fundamental thing about it. Because the buffer is now being shared across all the invocations of read byte, it's no longer thread safe. It's no longer safe for two things to call read byte at once, because then they conflict in their buffer. But there is a way that we can bring this together and kind of get the best of both worlds. And I won't go into this in depth. I want to keep moving on. But we can kind of take the best of both worlds. We can create a new kind of reader that has its own buffer, and it has its own buffer and an underlying reader. And then in the kind of reader next, give me the next character, it reuses its buffer, which is local to that instance. So we kind of have the best of both worlds. Rather than using a buffer allocated every time, we have one shared per instance. And now, as long as the buffered reader, the byte reader type created here isn't shared with anybody else, it's perfectly safe to reuse that buffer. Let me just go build. And just to demonstrate that this shouldn't really have any impact on, this is going to be called main3, an impact on performance. You can see it's roughly the same speed as before. All right, so that's CPU profiling, memory profiling. They're both part of the pprof family. Pprof is something that's been built into Go since the very earliest days. In fact, I can't think of a time when we didn't have it. But pprof, it's part of the runtime, but it's also somewhat stands aside. CPU profiling, for example, sets up an interrupt and just kind of stops the program and grabs all the stack traces and then puts it back going again. The next example I'm going to show you is one where pprof can't really help, and that will be an introduction to a different kind of profiling, which is also built into the Go runtime. So to talk about that and give a bit of setup, we have a program here written by Francesc Campoy, which creates Mandelbrots. Maybe some people know what the Mandelbrot set is. It's a fractal. Let me just quickly fix. I had some examples in there from earlier. Okay. So this makes little images, the classic Mandelbrot set, which always looks terrible on all kinds of presentations, but you can see this kind of fractal generated image. And the important things about this is is 1024 by 1024. This is a megapixel, 1 million pixel image. So that's what this program does. And again, we want to say how long did it take to do this? And potentially, is that the most efficient way we can do? So today, I've given this talk everywhere in the world, and depending on like how hot it is, like how well charged your battery is, you'll get answers from like 2.5 seconds to 1.8 seconds to 1.7. It's really, it just depends on a lot of environmental factors. But today, it's taking 1.7 seconds to compute a 1 million pixel image. We wanted to ask, well, can we do better? So let's apply the tools that we had from the previous presentation and have a look. Oops. So again, we're just setting up a CPU profile, putting it in the current working directory. Okay, and we can use the same tools to investigate that. Okay. It's always a pleasure to try and fit this on the screen. There we go. Well, let's talk about what we can see here. Obviously, there's a lot of the work. In fact, 83% is in fill pixel and paint. And there's some other stuff in here. We can zoom in a little bit. It's got something to do with PNG encoding, which kind of makes sense because once it's computed the image, we need to write it out. But let's focus on like the big rocks here and the big rocks in the stream, not the little stones, and say 83%, more than of the time is being spent in this function and the one that it calls. So if we want to have the most impact, we should improve those. So let's have a look. We can have a look at the source code for those two. Let's just make it a little bit bigger. This is fill pixel, and fill pixel is doing the Mandelbrot calculation, which is a calculation over a complex number, which is just trying to like say, does it reach this limit? That's how you kind of make a Mandelbrot. And then once it's computed the iteration count, which is the thing that gives the coloring, we then pass that to fill pixel, which actually paints on the pixel, say you will be this color. And so we have fill pixel and paint pixel. And we can see that paint pixel is spending about a second doing that collectively. There isn't a lot we can do there. Like it's just an assignment. And we can't not do this assignment because then we won't get any pixels on our image. So we kind of have to do this work, which is a bit disappointing because that pprof has told us where the problem is. Like it said, here's the problem right here. Like you're spending all your time here, but this is work that we need to do. We can't cache it, we can't reuse it, we can't buffer it. We have to do this work. So this is kind of the limit of where CPU profiling could take us. And so with that, I'm going to introduce a different kind of tool. And the name of the tool is the execution tracer. And it was written by Dmitry Vyakov in 2015, and it took a few years for people to figure out how to actually use this thing. In traditional engineering style, Dimitri landed it in the code base with no documentation and then went on to other things. And we can see when we run it, let me just do that again. We get a different kind of trace. Actually, let me just time that because we'll need that later. So you can see that one thing is that trace profiling has a different kind of impact on the performance of a program. It's not so much sampling based where it stops the program, but it's actually integrated into important parts of the runtime where it just kind of annotates things happen. So its performance overhead can be lower, but the compounding thing is, we'll see in a little bit, it can also generate a lot of data. So don't come away from this thinking, it's free tracing, we should always turn it on. But now we have a trace profile. We can have a look at that. Now, trace profiling is a little bit different to CPU profiling. We need a different tool for that. And what this tool is doing is it's actually translating the trace file that we created on the fly and translating it into something that Google Chrome's inspector knows how to do. So this is the generic Google Chrome inspector. We're just kind of reusing it and feeding it our own data. Now, some of the things that we see across the top here, I don't know if I can make it, make it a little bit bigger, is that we have a list of go routines, which is just a count of the number of go routines running. Heap, so if you're used to the classic kind of behavior of heap allocated languages, this should look pretty familiar. We have a list of threads. We have things for GC and syscall. And down here are what we call procs, is a historical name, don't really need to go into it, for CPU cores or threads. It's not actually threads, it's more cores. So this is an 8-core machine, so we could see up to 8 procs. The reason that there are only 6 on here is the others were just not used through the run of this program, so they just recorded no data. We'll see later on that they show up later. And so what we can see in this program is there are kind of 2 kinds of behavior. We have the big behavior over here on the left, and then there's a kind of a step change. We can see that kind of at this point, the heap usage starts to change. There's just kind of more things on the graph. We don't even need to get into what these represent. There's just kind of more of them. So there's a kind of a step change in the behavior. And one and what we're seeing here is, well, first of all, we spend all our time filling pixels, and then we pass off to PNG encoding them. And PNG encoding them is actually writing to a zip writer. So there's a step change in the behavior because we stopped doing one thing and started doing another thing. And depending on how well this program is behaving, sometimes it can be a little bit cantankerous. If you actually zoom into each of these things, you can ask it, like if you click on them, you'll usually get a stack trace. So we can confirm that behavior. We're seeing, a little bit smaller. We're seeing late in the picture, PNG encode, write DATs, write image, write out to compressed lib, which matches the profile that we saw before. So we're pretty confident that this bit at the start is obviously the computing the image, and the bit at the end is writing it out. And unlike the CPU profile, which we saw before, this is actually telling me quite a lot in terms of it's telling me there's something missing. And the clue is, well, there's only one of these green bars. We are using one CPU fully for close to a second and not using the other 7 at all. So perhaps one of the ways that we can improve the performance of this program is to do more work in parallel. We have Go routines, we could do more. And so if we look at the code, this the mode we're using core is called sequential fill image. For each row and each column in every row, call fill pixel. But we can do other things. For example, we can for each row and each column in every row, we can start a Go routine to compute that pixel. So let's just, 1 million Go routines is totally within the capabilities of the Go runtime. Let's just start them all, let the scheduler figure it out, and hopefully it will use all our cores. And the way that we do that with this program, because Francesc wrote it well, is we have a mode. We say mode pixel, which is per pixel. Let me just time that. Who thinks this is going to go well? Okay, that's interesting. So the real time, remember we were about 1.7 seconds before, real time's actually gone up. Okay, not what we were wanting, but if you note the user time is significantly more. It's significantly more than the real time. And this is, real time is what we perceive. It's the progression of time. User time is a kind of a counting figure for how many CPU seconds you used. If you've ever gone onto a machine and typed top and seen a process using like 500% CPU, that's because it's got 5 threads doing work within it. And so this is maybe an indication that we're doing a lot of work. We're doing more work. It just so happens we haven't actually improved the runtime. So let's have a look at the trace file. Now, you notice that this is taking a lot longer. And this is because the trace is a lot larger, because the costs of doing the trace are a function of the number of Go routines and their interactions. And because we have 1 million Go routines and 1 million interactions, we have the kind of Cartesian product of that. So that's why the trace is quite large. And I'm going to talk a little bit ahead of what's going to happen, because this will take a little bit of time. What we see, first of all, is, well, now the trace is so big that we can't load it all in one go. And this is a small limitation of the trace tool, which is actually a limitation of JavaScript, that you can't have a string bigger than 100 meg. The information that we're trying to pass into this tool is about 100 meg. Well, it's multiple megabytes. So there's some good stuff. This is just a little fragment of the trace, about 150 milliseconds of it, and at least there's activity across all of them. It looks like we're using more CPUs. That kind of matches what we saw here with our user figure. But if we actually zoom in, we look in closer and closer, it says there's an awful lot of holes here. And just in the interest of time, what we're seeing here is doing 1 pixel is not enough work compared to the overhead of like scheduling a Go routine and starting it up. If we look up over here to the kind of Go routines list, we wanted to start 1 million Go routines and kind of like work on them all the way down. But it seems that we never get more than a few runnable and a few running. And it's basically the amount of work to start and schedule that Go routine is more than the amount of work you actually get out of it. So we're spending all our time scheduling work and not any time doing any work. So this tool has other modes, and the one we're going to talk about next is if doing 1 pixel in a Go routine is too little, and doing all the pixels in 1 Go routine too much, what if we did a whole row? So we're going to do 1,000 times less work, 1,000 times less Go routines, but do 1,000 times more work in each Go routine. So the trace finished much quicker. See, this is the first time we've actually improved the performance. We're now nearly a quarter of the time it took. When we look at the trace, loaded straight away. So there's a lot less interactions. And that's kind of nice, because it means we can see the whole program. And this looks like the behavior that we want. Starting at the top, we have this big backlog of Go routines. We create all the Go routines, and then we sit and wait for them to all finish. So we can see as we go down here, you can see it's trending down. We're just working through the backlog. Here, the list of threads, 8 threads busy for this whole block. And then, of course, on the other side, we zoom into this. We kind of go into this different behavior of writing out the PNG. And if we zoom in here, we can see now that each of these different Go routines this is their work. This is their little bit. They live for the time to compute 1,000 pixels, and then they go away. So that's pretty good. We've now improved the performance of this program by at least a factor of 4. Now, there's some other ways we could do this. Rather than per pixel, we could start up a bunch of workers. So we know how many cores we have. We have 8 cores. We could start a bunch of workers and then pass work to them. Maybe that would be faster than using this kind of go-routine scheduling. So the way that we do that in this program is work. I need to remember the exact syntax. Workers, no, we say 8 workers. Okay, interesting. Let's compare that to the row mode. They're about the same. Okay, let's have to do the workers again just so I get the trace again. The trace. And so it's pretty much the same behavior. Whether we choose to run work in, just create a bunch of go routines and say, go schedule yourself when you're ready, or whether we create a bunch of dedicated workers and feed work to them, the result is pretty much the same. And how am I doing on time? I think I'm pretty close to time. So the one thing to leave you with, this is a very quick overview of the trace tool, but you can see that knowing nothing about the program, knowing nothing really about what it's doing, we were able to improve the performance by seeing that it wasn't using all the cores in the program, in the machine. We spread the work across it. And the thing I want you to think about is, we can see here we have 8 cores doing work. And you can see that now, roughly, it's about 50% computing the image, 50% writing it out. Now, logically, you could say, hey, look, if I got one of those 16 core Macs, then I could have 16 workers, and all things being equal, we could compress that down again to half of that what it was. You could think, well, if I run this on a giant server with maybe 64 cores, we can continue to do this work more. And then when we get to maybe 1,000 cores, well, we could rather than giving 1,000 pixels to each go routine, we could give 512 and continue to parallelize this work, because the Mandelbrot set is embarrassingly parallel. And this would, you could see, taking this to its logical extent, this side over here, we can effectively reduce it to effectively nothing. But the thing I want to leave you with is, what about this side? This is the more complicated problem of creating a compressed file, which is quite hard to parallelize. And the thing that I want to leave you with is that this is not a new idea. Gene Amdahl, who was one of the important figures in the IBM 360, talked about this in the 60s or 70s, and he coined this as Amdahl's law, where he said that the maximum speed up that you can expect in a program is limited by the sequential work. And we can see this one. Where's my graph here? Even if we throw as infinite parallelism at this part of the problem, the best we can do is only improve it by 50%, because we still have this sequential part on the right-hand side. And so to leave you with that, think about the programs that you write, and you might want to apply some parallelism to that. But if we look at Amdahl's numbers, to get even up into like 20 times speed up, you have to parallelize 95% of your program's total execution. That means only 5% of it can be sequential. That includes startup, reading from disk, any kind of like housekeeping activities that might your program have to interact on. And you think that's actually quite difficult. And this is one of the things that limits the amount of parallelism we can actually take advantage of, because of, unfortunately, Amdahl's law. So with that, I'm going to end. And if we have any time for questions, please shout them out.